Welcome back to The Explainer. Today, we are setting the stage to explore some of the hidden, dynamic rules that literally govern our physical world. When you look at a glass of water, or a rusting piece of iron, or really even just the air around us, it's so easy to take what we see at face value. We see a final result, a finished product, a totally static state. But as we're going to see today, nature is rarely as still as it seems. We're going to take a really close look at a phenomenon called chemical equilibrium. And honestly, it's a concept that completely rewires how we understand the way materials in our universe interact.
So I gotta start by asking you a question. Do chemical reactions ever really stop? When you bake a cake or, say, strike a match, it feels like a total one-way street, right? The ingredients transform, the reaction runs to completion, and then it just freezes. It's done. But hold on to this idea. What if I told you that in a ton of chemical systems, that final stillness is a complete illusion? What if, instead of stopping, these chemicals actually enter into a vibrant, ongoing, completely invisible dance? Part 1. The Illusion of Stillness, the Secret Life of Reversible Reactions. Okay, let's just dive right into this. To the naked eye, everything in a closed chemical system might look entirely stationary. You put some reactants in a flask, you wait, the color stops changing, the bubbling dies down, and you think, okay, the reaction is over. But underneath, at the molecular level, things are moving furiously. The products that just formed are actually reverting back into the original reactants right in front of you. We call this dynamic equilibrium. It happens when the rate of the forward reaction, so the reactants turning into products, perfectly matches the rate of the reverse reaction, where products turn back into reactants. Because these two rates are exactly equal and opposite, the overall concentrations of everything in that flask stay completely constant. Both reactants and products are just hanging out there at all times. It's a continuous, super busy two-way street. If you're trying to picture this, our source material offers a fantastic analogy. Imagine you're at the mall and you try to run up the down escalator. If you match your upward speed perfectly to the escalator's downward speed, well, to anyone watching you from the mall floor, you appear to be standing completely still. You aren't getting any closer to the top, and you aren't falling to the bottom. Your position is constant, but your legs are working furiously. And that is exactly what a chemical system in dynamic equilibrium is doing. And this brilliantly illustrates the physics behind why this actually happens. Think of it like a U-shaped valley. This is the Gibbs free energy curve. As suggested by J.W. Gibbs way back in 1873, a chemical system will naturally seek the lowest available energy state. The reaction naturally progresses from pure reactants on one side or pure products on the other, straight down toward the bottom. That stationary point right at the bottom of the valley, where the derivative of the Gibbs energy vanishes, meaning the slope is exactly zero, that is equilibrium. The system settles in the valley because there's simply no more excess free energy driving it in either direction. Section 2. The Law of Mass Action, the Math of Perfect Balance. Which leads us to a pretty crucial question. If this crazy dynamic balance exists, can we actually measure it? Can we predict it? And the answer is absolutely yes. Thanks to scientists Goldberg and Waj, who came up with what we call the Law of Mass Action, we actually have the mathematical tools to define this perfect state of balance. Whether we're dealing with partial pressures for gases, which is Kp, or concentrations in solutions, known as Kc, the structure is exactly the same. This K is the equilibrium constant. It's fundamentally just a ratio of the products raised to the power of their coefficients divided by the reactants. This mathematical constant defines the system's exact final resting point at a very specific temperature. Once the system hits equilibrium, boom, this ratio stays locked in. So what does this math actually mean for us in the real world? Well, it gives us instant visual intuition about the mixture we're dealing with. If our K value is greater than 1, it means the numerator, the products, is larger. So we can expect a heavy concentration of products at equilibrium. But if K is less than 1, the denominator, the reactants, dominates. The system heavily favors the reactants and honestly hardly produces anything new before settling into its balance. But here is where it gets really fun. What if our system hasn't reached the bottom of that energy valley quite yet? Enter Q, the reaction quotient. Now, the formula for Q is exactly the same as K, but we plug in the numbers at any random given moment, not just at equilibrium. You can kind of think of Q as the system's current location on a map, while K is the system's ultimate final destination. So the absolutely crucial point is this. By comparing where we are right now, Q, to where we want to be, K, we can predict exactly what these chemicals are going to do. If Q is less than K, the system has a negative change in free energy and will forcefully drive the reaction forward to make more products. But if Q is greater than K, the system has overshot its target. and the reaction will spontaneously run in reverse to make more reactants until Q finally equals K, and equilibrium is achieved. Section 3. Disturbing the peace, testing the limits of equilibrium. All right, so now that we have our perfectly balanced, mathematically predictable system sitting happily at the bottom of its energy valley, what happens when we mess with it? What happens when we subject this beautifully balanced system to outside stress? Let's disturb the peace a little. Back in 1884, a French chemist named Henri Le Chatelier actually formulated a principle to answer exactly that. Le Chatelier's principle basically states that if a chemical reaction is at equilibrium and it experiences a change in the conditions that affect that equilibrium, the position of the equilibrium shifts in the opposite direction to offset the change. In short, the system absolutely hates being disturbed and will immediately try to counteract whatever you just did to it. According to our sources, there are 3 primary ways we can effectively stress test a chemical reaction. We can mess with the concentration, by adding or removing chemicals. We can mess with the pressure or volume, which is a big one for gases. Or we can mess with the temperature by heating the whole system up or cooling it down. Section 4. Restoring the balance, how the system fights back. Let's actually see how this plays out in real time. We're going to apply these stressors and watch exactly how the system fights back to restore its balance. Let's look at concentration first. Step 1. You aggressively dump more product into a flask that's already at equilibrium. Step 2. Because you added product to the numerator of our equation, your current location, Q, suddenly spikes and rises above K. Step 3. The system is now completely out of balance, so it responds by shifting in reverse. It aggressively consumes that extra product you just added, turning it back into reactants until Q falls back down and perfectly matches K once again. Okay, now let's try pressure. Imagine a closed container filled with gases at equilibrium. Step 1. You push down on a piston, drastically increasing the pressure and decreasing the volume. Step 2. Suddenly, all those gaseous particles are incredibly crowded. They're under immense stress. Step 3. How does the system offset this? Well, it adapts by shifting the reaction toward the side of the chemical equation that naturally has fewer gaseous molecules. It literally shrinks its footprint to relieve the crowding in this newly cramped environment. Now, what's really fascinating here is a direct quote from our source materials. Le Chatelier's principle is no more than a useful guide. It doesn't explain anything. Now, why on earth would they say that? Because the principle is just a convenient shortcut for human observation. The real why is always driven by the underlying math and physics. The system isn't consciously deciding to shift. It's simply the mathematical reality of Q striving to equal K, and the system shedding excess Gibbs free energy to find the bottom of that valley once again. Which leaves us here. We've explored the hidden, dynamic, two-way street of chemical equilibrium. We've seen the mathematical laws that govern it and exactly how it fights back against stress. But why does this actually matter to you? Because the entire world of chemical engineering, from synthesizing fertilizers to feed billions of people, to optimizing the batteries in our phones, to capturing carbon from the atmosphere, relies entirely on manipulating these very rules. How can mastering this invisible balance help us engineer better solutions to global challenges? By understanding that nature is never truly still, we learn how to dance along with it. Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll catch you next time.